All right, so as we talk about impulse and momentum, impulse, we can approximate, we know technically it's the integral of the force with respect to time, though we can approximate it as the average force applied in that short time frame that we're representing as the impulse. But we can also say impulse is a change in momentum. Momentum final minus momentum initial, but momentum is m times v, mass times velocity, so we could write this as mass times velocity initial. So two ways of describing this. We're going to look at a number of problems involving what we consider a collision, or problems we can consider an explosion. The explosions we're doing will not be Hollywood level explosions. We're talking something that breaks apart into 2 pieces or 3 pieces, something very mild and small. Let's talk, for example, about a simple fender bender. If one car rear-ending another. So let's say we have 2 cars. I'm just going to draw them as dots because we're still technically in the particle model. Everything is still considered a dot right now because we're not going to account for any rotational motion yet. That is in the next section. So let's say we have a car 1, traveling to the right with some speed, v1 initial, and they're not paying attention to what they're doing, and they don't notice car 2 ahead of them is traveling slower than they are. So let me make this a little more obvious for vectors. If they don't notice, and therefore they don't slow down, car 1's going to rear end car 2. So that's what I mean by a fender bender. We run into each other. Well, potentially. Well, as car 1 pushes on car 2, car 2 experiences an impulse, right? It has a force from car 1 applied for a small period of time. We could write that also as the change in momentum of car 1. Car 2. What that means is if I was to look at just a split second later, car 2's velocity will be different. I don't know if you have experience with this, but if you're the one being hit from behind, that will cause you to move forward faster, at least for a really short period of time, right? Because the force that car experiences, if I were to draw the force on this car, the force would be to the right. That force would cause an acceleration, so it would make the car speed up. Now, we don't mean speed up over a long period of time. We're not going to be continually, whoever's in car 1 is not going to continue pressing on the gas and try to push the car off the road in like a movie. We mean just running into each other and then the whole panic of, oh no, what just happened? So by V final here, I mean immediately after the collision. We're accounting only for the force that car 1 is exerting on car 2. We're considering this that impulsive force, that force applied for a very, very short time. Okay, so car 2 experiences an impulse because the force of car 1 acting on it, which means it has a change in momentum. But according to our friend Sir Isaac, if car 1 pushes on car 2, Then car 2 pushes on car 1. That push is opposite in direction, but the same magnitude of force. That means car 1 also is experiencing an impulse because of this collision. The impulse it's experiencing is, I'm writing it as negative F to account for it pointing to the left, in comparison to car 2's being positive F. The magnitude of this impulse is the same. Now, of course, car 2's impulse is to the left, while car 2's impulse is to the right, while car 1's impulse is to the left. It's just the direction the force is in. Because car 1 is experiencing an impulse, that means its momentum is changing. So if we wanted to, we could say car 1 and car 2 together, these represent a system. The system meaning the objects that are interacting, that are in contact, causing changes in velocities because of this collision specifically. The overall impulse on the system would be the impulse on car 1 plus the impulse on car 2. But if we think of that in terms of force and time, those will add to be 0. They add to be 0 because the force that car 1 exerts on car 2 is the same as the force that car 2 exerts on car 1. And it's the same amount of time. If we write this in terms of adding these changes in momentum, we end up with this relationship saying that the change in momentum that car 1 experiences plus the change in momentum that car 2 experiences, those have to add up to be 0 because their momenta are only changing due to the forces they exert on each other. This is considered conservation of momentum. Technically linear momentum, but this is the only type of momentum we have right now. So linear. If you think about conservation, we've used that term already for conservation of energy. What we meant by that is all the energy that was in the system initially had to be there finally, somehow. That's ultimately what we mean here as well. But we're limited in that momentum is conserved only when the net force on the system is 0. That doesn't mean there's no forces. It just means the forces involved in changing the momenta of the individual objects during the collision, those forces are from each other. They're exerting forces on each other. So if we add car 1's force to the right and car 2's force to the left, they add up to be 0, meaning a net force of 0 on the system as a whole. We cannot include the time where friction is acting or outside, meaning external forces are acting. If any force from something outside of the system is acting, even gravity, for example, then the net force would not be zero on the system. And we would not be able to use conservation of momentum. So conservation of momentum means same amount of momentum that all the objects in the system together have initially still has to be there in the form of momentum finally. Let me write this a little differently so it has a similar setup to energy. By momentum, or change in momentum, we mean P1 final minus P1 initial. That's what we mean by delta P1. But then we also have delta P2, so P2 final minus P2 initial. All of this has to add up to be zero. If I bring initial stuff to the same side, that leaves the final stuff on the other side. In this form, it looks closer to, not the same quantities, but conservation of energy in that the initial momentum in the system. So every object within the system, in the case of these two cars, just the two cars, that initial moment in the system still has to be the same overall final momentum in the system. The overall momentum has to stay constant during the collision itself. How much momentum is in the system depends upon the mass and velocity of car 1 and car 2. We would be adding these two together to find the total momentum in the system initially. It still has to be there finally, but what's going to happen is these velocities are going to change. The V1 final is now smaller than it was before, but V2 final is bigger than it was before. They have to add up to be the same thing. Now, that doesn't mean the velocity car 1 loses is the velocity car 1 gains. That's not the case. We have to consider the momentum as a whole, meaning mass times velocity. So the momentum car 1 loses is the momentum car 1 gains. In the test notes, you're going to see near the conservation of energy, momentum, it simply says P initial equals P final for the system. In any problem that we're going to apply conservation of momentum for, we need, number one, to define the system. How many objects, which objects are involved in the collision, or if it's something breaking apart, how many pieces does it break into? That's what we mean by an explosion. So we need to identify all objects involved in the collision or explosion. That's ultimately when we can say momentum is going to be conserved. A collision, as long as we're accounting only for the tiny time frame where that impulse of force between the objects is involved, then momentum has to be conserved, which is awesome. What we mean by momentum initial is just how many objects. In the case of the cars, momentum initial became P1 initial plus P2 initial. There were 2 objects involved in this collision, so P initial for the system simply means P1 initial plus P2 initial. Similarly, P final means P1 final plus P2 final. If there were 3 objects involved in the collision, then you would just add P1 plus P2 plus P3. Technically, we could go on forever with that, which of course we're not going to. We'll stick to 2 or 3 objects. This momentum is awesome because it's a very simple way. If I plugged in for mass times velocity, this is a very relatively, I should say, simple way to relate the mass of these 2 cars to their initial and final velocities, right before the collision to right after. This equation, conservation of momentum, must be conserved if there's no net force on the system. Meaning, it's always conserved in collisions. Anything running into something else, momentum will be conserved as long as we can isolate and look at just those 2 objects and they are not, neither one of them are interacting with anything else in that really tiny time frame. It's very cool. Explosions, momentum will always be conserved. So as a general rule, as you are looking at problems, if your problem involves a collision, but not with a spring, with only a spring, I should say, because we've done some examples, only a spring, sorry. We did examples with energy. We can account for a box running into a spring using energy. And that's still true. And technically that's a collision. Or if we have a box compressed against a spring and we let it go, the spring pushes out, the box will leave the spring, that would be considered an explosion. So if you have one object with a spring, just use energy like we have been doing. If you have more than one object, then, and they collide, or they come apart somehow, that is where we're going to group it into what we're calling a collision or explosion, and we will look at conservation of momentum specifically. We'll do some example problems as we go along.